Hello, so welcome back. So we are looking at the implementation of a 5 by 5 matrix machine, and basically this is a sample project for digital logic design. And if you look at what we are going to implement, we are going to implement a system that looks kind of like this. We have LEDs that have been arranged in a 5 by 5 manner. So we have different states that we need to implement. We have state zero. So at state zero, it means that all the LEDs are off. Then we have state one, where the LEDs on uh, this column are on. And then state two is this. This is state three, state four, state five, like that up to state 15. So those are the steps that we are supposed to be implementing. Now I have written these letters here so that they can represent the LEDs that we are having. So, for example, the first LED in this figure here, the first LED of this figure is this LED here, and it is being represented by letter A. And the second is this one, it's being represented by letter B. And that is how we represent all the LEDs by using these letters. So what we're going to do is we are creating a table, which is a truth table up here. And this truth table, we have states running from 0 up to 6, because these are the maximum number of states that we have as per what we have been given in exams, which is this one. So basically, if you look at this uh, state sequence here, then it means that we are going to implement state 8, then we implement state 12 or state 14. State 12 or state 14, in this case, or means that we are implementing them at the same time. And then we proceed to state 3, and then we proceed to state 13 or state 11, meaning that state 13 and state 11 are being implemented at the same time. And then we proceed to state 5 and state 6, meaning that we are implementing the intersection of 5 and 6 only, and the rest of the LEDs should be off. And then state 4 and state 7 means that we are also implementing the intersection of state 4 and state 7. Then we have state 3 and state 8, also means that we are implementing the intersection of state 3 and state 8. And that's how we are going to implement this step sequence here. So what I did is I represented all these LEDs. I put them in my truth table from A to Y, and there are 25 of them because it's a 5 by 5. So I will look at the behavior of all these LEDs beginning from state 8. So if I come to my LED states, state 8 is this state here. And you realize that in state 8, the LEDs that are on are these LEDs that are in the middle here. So what I'll do is that in my letters, I'll check the letters that correspond to these LEDs, which are these letters here. So it is K, L, M, and N, then O. These are the LEDs that are on in that state. So what I will be doing is I'll come to this table, then where we have K, L, M, N, and O, I put all of them on. And in digital logic design, on means 1. So I will come to K. So this is 1, 1, 1, 1, and 1. So those are on states. Then I will do that for the rest uh, of the states that I'm supposed to be implementing here. Don't forget that when we have this stroke, it means that state 12 and state 14 are being implemented at the same time. So you have to make sure that you put the ones for state 12 and also the ones for state 14. Otherwise, the rest of the LEDs become zero values. And we proceed like that across all of them. And that's how our truth table will look like once we've finished all the steps. Now, the next step is normally to generate the logic expression by use filling in the kernel maps. Now, if you look at these kernel maps, what we do is we fill them in this order. You fill this, 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 and this. It's not a new concept because if you watch the previous videos, then you'll clearly see that uh, there is a pattern that is being followed when we fill in the kernel maps, and depending on where you placed your A, B, C, and D values. So this is what's happening. So for example, if I am to give an example with the first kernel map, which is this one, then what I'm going to do is I will look at state A, which is this one, and then here I am filling in 0, 1, 0, 0. So I'll come here and fill 0, 1, 0, 0. Then the next one is 0, 0, 0. So I'll fill in here 0, 0, 0. And then the rest of the unfilled cells are don't care terms, and that's why I fill them in with x, 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 x. And that's how this kernel map is being filled. So we do the same for the rest of the kernel maps. So then after we've done that, then we have to group our filled in values, and we normally look at the largest groups possible, and then we also try to get the smallest number of groups possible. And when you do that with all these kernel maps, then you get the following logic expressions. But just to give you an example with this one here, how I came up with A, B prime, C prime is that I will group the values that are having ones, for instance, and the largest group I can get in this case is this value here. I check where it belongs. So it is fully in A. That's why I have this A. Then it is not in B. It is fully out of B. So that's why it's B prime. And it is fully out of C. And that's why it's C prime. We do the same for the rest of the kernel maps. So another thing is if you see that in an LED we have zero values from up to down, then it means that the value of that LED is zero. So it will literally be connected to an input signal that doesn't have a current flowing through it or doesn't have a signal flowing through it. So that's how we represent them. So when you see that all of them are zero, just replace that value with zero. Then we have to begin the implementation of this project in our Hades software. So one of the things you need to note here is that this is a project that combines both sequential logic designs and combinational logic designs. So when we begin by sequential logic designs, then it means that we have to first create a counter. And in this case, our counter is counting from 0 to 6, then going back to 0 and again to 6, and that continues like that. So if you want to know how to design this counter, you can go to one of my videos that explains how to design the counter circuit, and then you watch all of it. Then you can implement the counter and continue working on this project. The next thing that we need to do is to generate the circuit of this, the combinational circuit of this project. So how the combinational circuit is going to look like. So basically what I've done is I've created a series of these LEDs here, and I'll put them in the manner in which they're supposed to be arranged in that matrix. And that's why we are having all these LEDs. And then I've also looked at my logic expressions from the kernel maps that I filled in, and I can see the mean terms that I'm having. For example, in A, I can see that in A, I have A, B prime, C prime. This is obviously a three input AND gate. So we create a three input AND gate that have got different combinations depending on the numbers that we have. And that's how we came up with um, A, B prime, C prime, A prime, B, C prime, A prime, B prime, C, and A prime, B prime, C prime. So that's how you come up with them. But the two input AND gates are also available. If you check at the logic expressions that we've created, then you realize that some of the min terms are two inputs, like this is AC, AB, and maybe very many others. And also we have min terms that only comprise of single values, like this is C prime and this is B. You don't need to create any AND gate for it, or the only thing that you need to do is to combine them using OR gate, and you're going to see how that one works. After that, when you come to this, you create the OR gates. The OR gates are supposed to be combining the min terms. So for example, if we take an example of this first OR gate, looking at this part here, we notice that, for example, in I, the kernel map for I, the logic expression is I is equal to AC plus AB, which is AC or AB. So if we want to implement this, then we have to create an OR gate, and the OR gate is this. Then we combine the values of AB and AC. So AB is the AND gate that had the combination of A and B. Then AC is the AND gate that has the combination of A and C, and that's how we combine both this and this, the outputs to the inputs of this OR gate, and that's how we come up with that. Then after that, we do the basic wiring, wire everything. Here we have the inputs, input switches, then their negated values. So if it is D, you check where D is, connect all the wires, and if we have the D prime, also check where the D prime is, connect all the wires, and that's all. So once the whole of this is done, you can begin testing if at all it's working the way that you want. So you can activate all the input switches. You have the first pattern is this one when the state is 0, and it is the same as what we saw here, because we saw that our first pattern is supposed to be given by state 8. If you check our state 8 here, then the LEDs that are on are the middle LEDs. And that's why here, when we are at state 0, we have these LEDs here as on. Then the next state is state 1. If you click 1, then you see that these ones are on. Now these values are this, this, and this. Then we have this, this, and this. So we can check which values were on. If you look at this one, it was 12 or 14. Now 12 is this one here, 14 is this one here. If you combine all of them, then you get this diagonal line of LEDs being on. And that's the reason why here we have the all of these ones as on. Then 2 is this. The middle vertical LEDs are on, all of them. So if you come here and you check that, you realize that it is given by these three here, which is this one. And you continue the same for the rest of them. So if you check 3 is that one, then you check 4 is that, 5 is this, 6 is this, 7 is the last one. Though we don't need 7 because our scripts are being implemented up to 6. So 7 is a don't care term. We don't really care about it. And then the process repeats itself. So once you're done with this, you need to create the symbol of this as well. So you come here, edit, and then you create symbol. Then you will be done with the combinational design. So what we need to do is we need to combine both the combinational part and the sequential part. Then we drag the LEDs and we see how it's working. So I'll come to File, then New File. So I'll right click, create sub-design. I will pick the combinational part. So this is my combinational part. Then I also pick the sequential part. So right click, create sub-design, and then take this maybe just move it up a little bit, and then maybe zoom it out. I'll just zoom this region so that we see what's happening. So I will connect D out to D, C out to C, B out to B, and A out to A. Now this other side, I will put my clock generator. So I'll create IO clock generator. I'll put it somewhere here. Then I'll create my set button IO pin switch, and I'll put it here. So this pin switch is the set, and this clock generator is the clock. So I'll name this as clock, and I'll name this as set. Now what I need to do on this other side, I need to drag some LEDs and also arrange them in the same pattern that we have in the matrix. So what I'll do is on this side, I'll create IO then I will use the LEDs, and then I will have them arranged here. So I'll have this. So I'll arrange them like that and then arrange the rest of them. So after I've arranged all the LEDs like this, I need to name these LEDs. So these LEDs, the first one is A, then B, C, D, E, F, G, as we go through up to Y. So once I've finished naming all of them, then I just need to connect every single one of these ports to the respective LED. So I have the first one here as A, then I have this as have B. So once the connection is done, you can come and set your stuffs, the clock signal. If the clock signals is on, the set button is on, then your pattern will begin implementing like that. So that's how your 5x5 matrix is supposed to be designed using both the sequential and combinational logic circuits. So once this project is finished, then you need to save this circuit. So Control plus S, I'll save this as the test.hds. So you can check with the other circuits. So that's the combinational, this is the test, the combinational design is this. Then the sequential design, of course, is the counter, which is this. And if you want to check the counter test, which is not really important in this case, but you can check it, it's also this one. So you can check how the counter is working, but it's not really important in this project because I explained this in a different video, but you need it so that you can implement the sequential part. So once the whole work is done, you can come and change the directories that you have for this project. So I'll come to this part here and find all the files that I've created. They are in this thing. If I check the tests, so for example, this counter test.hds, if I double click this, it will prompt me to open it. I can open using a notepad. So just once, then I will go to my directory, file directory. So it is in this line here. So I can come to the last slash, which is counter.hds. From here, I can delete everything in that directory and replace it with a dot. Then I save by Control plus S. And after that, I can exit that notepad. I come to the test.hds also here, open using a notepad. Just once, this is how it looks like, and my directory is here. So I can come to this last slash. I can delete this path to this directory and replace it with a zero, sorry, with a dot, and then Control plus S, and that one is also saved. We are done changing the directories of all the tasks. What we need to do is we have to create our folder as a zip folder. It means that we have to submit our project as a zip file because we don't want it to occupy a lot of space in the professor's laptop. So I'll come back here, then right click on this and compress this to a zip file. So that's all for this project. See you in my next video.